Hi there. Now, regarding porosity logs, we will be discussing in this occasion our neutron porosity tool. So, just a recap about what is porosity. It is denoted first by the Greek letter phi, this one, and it refers to the fractional volume of void space in a bulk volume of rock. So, with this picture, we will be able to see it better. Imagine in these images, the yellow area is solid rock, and the blue is void space that hopefully will be filled with hydrocarbons. So the fraction of the blue area will regarding or compared to the solid rock that will be defined as porosity. And why is it important? Because we need it to have a place for hydrocarbons to be there. Now, our neutron porosity tool might look like this. Obviously, this will change on each service company. This is just one of many models, but in general terms, it is a tubular with very few movable parts. It just needs a place to put the radioactive source on it, the neutron source. And this model, this is the cavity where the radioactive source is put. And this is how the neutron radioactive source look like. Remember that when working with radioactive material, special safety measurements should be taken. In this case, the area is surveyed with these instruments. These are the survey meters to measure radiation. And in this other picture, we have an accessory, which is usually run with a neutron tool, is a decentralizer. Later on, we will be discussing why is it necessary. But in first place, why running a neutron porosity tool? The main purpose is to estimate total porosity. It would help us determine also the lithology used with another porosity tool. This is important to keep in mind that the neutron porosity tool is usually, almost always, run with a density porosity tool. Another application is the identification of gas-bearing formations. Okay, in this image we will discuss how do we convert neutrons that are being emitted by a radioactive source to porosity measurements. So this red dot will be the neutron generated by our source. Once it leaves the source, that neutron will start interacting with the atoms in the formation. On each collision, that neutron will lose some of its energy. So here we have this neutron, had a collision, then it moved forward, had another collision, and so on. When they leave the radioactive source, they're high energy neutrons. After many collisions, their energy level will reach a thermal level. And what we mean by a thermal level? An energy level of 0.025 electron volts. And once this neutron becomes thermal, then that neutron will be able to be detected by the detectors of our neutron density tool. Also, we should mention that another neutrons will, once they reach the thermal level, they will continue to interact with the formation, and some of them will be captured by the atom and create a gamma ray. But what is really being measured by the tool is a count rate associated with neutrons on a thermal energy level. And this is what I mean by a thermal energy level. Everything less than 0.1 electron volts. Okay, these factors are really important when considering the interactions of a neutron with the atoms in the formation. We will be hearing these two key concepts, the slowing down cross-section and the captured cross-section. So this slowing down cross-section is the probability that an atom in the formation will slow down the energy level of a neutron to a thermal level. And the captured cross-section is the probability that an atom will absorb a neutron with low energy level. Now, considering the factors affecting the measurements, here we have an example of a neutron tool, one in open hole, one in case hole. Here you can see the bow spring centralizer that we were discussing, and this is the purpose of why using that decentralizer. We want to compensate the detector standoff. The standoff is any physical distance between the detector and the formation. So what we want in this case is to make this space as small as possible. To have better readings. So let's remember that our neutron porosity tool will, in most cases, will be run with the density tool as well. And when checking a density log, you must check, or you must first consider or know that a matrix is being assumed. In this case, if you see here, we have neutron porosity lime, which refers to limestone, and density porosity 2.71. This is the same as limestone. This is the density expressed in grams per cubic centimeters. So the most general or common approach would be to think that if both tools read the same, assuming this matrix, odds are that they are right. So we might assume that on this formation we're talking about limestone because neutron and density both read the same. Another interesting aspect is just to keep in mind that whenever you want to determine porosity, you must make certain assumptions. So you must assume a formation matrix, and you should make assumptions regarding to the type of fluid within that formation. In the case of neutron porosity, fresh water is always being assumed. Here we have common responses. These terms you will be hearing very often. A stacked response is when the density from your density tool and the porosity of your density tool and the porosity of your neutron tool reads the same. That is referred as a stacked response, like this one. Now, a crossover is this scenario when porosity from the density tool is higher than porosity from your neutron tools, and separation is the opposite. Let's see. On this case, on shale, porosity, your neutron porosity will be reading higher. So that will be separation. On this case, this explains why this 2.71 is the same as limestone. If we were assuming a sandstone matrix, we should use these values. And the PE, well, actually this value comes from the density tool, but I just put it to have a reference because you can see the PE curve on this slide. So that was the basic of a neutron porosity tool. Thanks for watching.